All right, good evening. Welcome, everybody. I'm Doug Zemeckis, the Marine Extension Agent with Rutgers Cooperative Extension. Thanks for joining us tonight for our Earth Day Everyday Program Fall Seminar Series. Our theme this fall is What a Wonderful World, an environmental jukebox for New Jersey. Hope you appreciate the puns and the music theme to help provide science-based education on 4 different topics this fall, a mixture of ocean and land-based topics. Tonight, our theme song is Rock You Like a Hurricane. We have Dr. Travis Miles from Rutgers University, who's going to be presenting about hurricane science, ocean hurricane interactions. And I'd also like to acknowledge, and joining us tonight is co-pilots, serving as co-hosts. We have Dr. Steve Urjo, Sal Mangiafico, and Amy Rowe. My colleagues as other extension agents with Rutgers Cooperative Extension to help prepare and deliver this Earth Day Everyday seminar series. Some navigational aids for tonight's webinar. We have it planned for an hour. We have one speaker with Travis Miles. About 30 to 40 minutes will be his presentation tonight, and then we'll have Q&A at the end after his presentation. If you have questions for Travis, please type them in the chat directly to me. I'll be serving as host and moderator during the Q&A period. I will be organizing all the questions, and we'll get through as many as we can, but we expect about 15 or 20 minutes for Q&A, so hopefully we'll get through everybody's questions tonight. Travis, next slide, please. At the end of Travis's presentation, I'm going to launch a poll to get your feedback on tonight's program, what you learned, and what you'll hopefully do with what you learned this evening from Travis's presentation. That program evaluation survey, as well as a follow-up that will ask you about 6 to 12 months afterwards of how you will hopefully use what you learned tonight. It is considered research by our Rutgers Institutional Review Board. Therefore, you are considered human subjects in this survey and research project to get your feedback on tonight's program. There is a short program evaluation survey at the end that I'll launch as a poll. There's 10 questions. We hope that you will take that brief survey and provide your feedback tonight. But the first question is, do you provide your consent to participate in that survey? If you are interested and willing to provide your feedback, please answer yes. If not, you can select no. If you have any questions about the survey and the program evaluation, you can contact our colleague and co-organizer of this program, Dr. Amy Rowe. Next slide, please, Travis. Also, Rutgers Cooperative Extension, we are an equal opportunity employer and program provider, providing science-based educational programs for clientele throughout New Jersey without discrimination, and making it as available as possible to as many as we can. Tonight we are live via webinar, but we are recording, and we'll post this recording on Rutgers NJES YouTube page that will share with you the links once we get it recorded with the other ones from this fall to make it available to everybody as openly as possible, free of charge tonight and on YouTube. With that, next slide, please, Travis. I would like to formally welcome, thank, and introduce our guest speaker tonight, Dr. Travis Miles. He's an associate professor at the Department of Marine and Coastal Sciences here at Rutgers University. He's been on the faculty for 10 years and at Rutgers for about 16 years after working on and completing his PhD here at Rutgers University in the Department of Marine and Coastal Sciences. So a great deal of experiences in oceanography here studying at Rutgers, and he got his bachelor's and master's at North Carolina State. So a variety of experience on the East Coast, but around the world. His primary expertise is studying the connections between the ocean and the atmosphere and how it influences ecosystems and a variety of marine life from plankton all the way up to fish and whales. Here at Rutgers, he's affiliated with RU Cool, the Center for Ocean Observing Leadership, that work around the world, but a lot in the East Coast of the US and in the Atlantic. Some of Travis's primary areas of research include studying the interactions between ice and ocean, sea ice in the ocean, studying the wind resource off New Jersey and elsewhere. And connected to that, a lot of his time is spent on hurricane science, really novel methods for observing the ocean, observing hurricanes, how they interact to improve forecasts. Uh, and that is going to be the focus of his presentation tonight, as under the theme of "Rock You Like a Hurricane," which I trust we will be rocked by his awesome presentation tonight. So Travis, thank you for joining us. I will turn the controls over to you.
Absolutely. Thanks, Doug. And thanks for having me to the entire group. It's a great opportunity to talk to this many people on a Monday evening. So today I'm going to talk about hurricanes, a little bit about how they work, a little bit about how they're changing, but also I'm going to spend some time on how we observe them using different ocean observing platforms. So I'm just going to jump right into it. I think you all know we're from Rutgers. I'm from Rutgers. I want to highlight that I am at the main campus in New Brunswick. So I'm an associate professor there in the Rutgers University Center for Ocean Observing Leadership. Are you cool? And despite all of the technology and cool science that we're doing, the picture I have here is the most important part of what I do every day. So these are students here in the cool room, the Coastal Ocean Observing Lab at Rutgers in New Brunswick. And this group was started about 30 years ago with the in New Brunswick in an urban campus with the idea that, if we can't bring every student at Rutgers or every student in our program out to the ocean, we certainly can bring the ocean to them. So this room is where we bring in all of our data. It's where our master's and undergraduate students work. Sometimes we'll just, if something interesting is happening in the ocean, we will drop our lectures and we will start talking about it, including hurricanes and tropical cyclones. Um, so uh, yeah, it's been a great place to work. I've been a tenure track faculty since 2018 and hopefully going to be there a lot longer working on this kind of stuff. So we work on a lot of different themes from ecosystems, physics, fisheries. What I'm going to talk about today is going to be hurricanes. So over the past 50 years, we've had about 2,000 disasters attributed to tropical cyclones or hurricanes. I'm going to use those words interchangeably, but I mean the same thing. Um, Over that time, about 800,000 people have been killed from tropical cyclones. That's an average of about 43 deaths per day as of 2021. If we think back, well, there's a storm in the Philippines right now that's really just damaged the Philippines quite badly the last couple of days. And then I'll show a little bit from Jamaica. This just a few weeks ago was impacted by Hurricane Melissa. But just in 2008, a single storm in the Bay of Bengal killed about 138,000 people. So just, thinking back, that's not that long ago, and we're still having disasters of that type related to tropical cyclones. In the US, it's mostly damages, not deaths, though there are still quite a lot of fatalities. The U.S. is definitely has the most damages due to tropical cyclones in the world. So in U.S. dollars since 1980, there's been 1.6 trillion in economic losses and damages from tropical cyclones. Um, those have been generally increasing. So this is damages, number of events on the y-axis per year, and then time on the x-axis on the bottom. And the red bars are the costs of each storms or all the storms in a given year. And then the lines don't worry about too much. Basically, what we can see is they're generally increasing. You'll notice Hurricane Sandy, which was in 2012, is not actually on here because it wasn't designated a hurricane at the time. It was actually a super storm or a storm as it made landfall, but Hurricane Irene the year before is on here. And so it's quite a significant problem. And if we think about New Jersey specifically, about 90% or between 80 and 90% of our natural disaster damages in New Jersey are actually coming from tropical cyclones and hurricanes. So we may not think about that. We may think about places like Florida or further south. But generally, we're having a lot of economic losses, mainly because we have a lot of coastal infrastructure. So even weak storms can have quite a big impact, just like Ida. or even the rainstorms last week. That wasn't a hurricane, but still we're getting a lot of flooding impacts. So it's definitely an important thing for us in New Jersey, and is one of the reasons I've been focusing on it for a while. So damages are getting a little bit worse. Some of that's due to sea level rise, development, but also storms are getting a little bit stronger. So this is an image or a plot of ecosystem. Well, this paper was about ecosystem damage by increasing tropical cyclones. And basically, what I want you to focus on here, this is like the number of storms per year of really strong storms, category 4 or 5. So we define storms by their category, with 4 and 5 being the strongest, but 4 and 5 being major. Generally, we're getting more storms every year over time. And the wind speeds themselves, the actual wind strength has been going up year over year. So it's an increasing problem. Some of that is due to one really important piece of hurricanes that I'll get into in a little bit, but it's that our oceans are basically the heat source for hurricanes. And I'll show that again. We had a scientist from Climate Central at Rutgers a few weeks ago, and I was looking at Hurricane Melissa in particular. And they came up with basically this method to attribute hurricane intensities, how much more likely a storm or an ocean temperature or something might be due to climate change. And for example, for Hurricane Melissa, this was one of the most powerful storms to ever make landfall in the Atlantic, definitely in Jamaica. So it was I think like they had a measurement of like 200 mile per hour winds at one point during that storm from one measurement. But generally, they did an analysis and they showed that the ocean temperature at this location was at least 800 times more likely how hot it was due to climate change. So the temperature at this location was about a degree C, 1 degree Celsius higher than normal, which can be quite a lot for these storms that basically soak up a lot of energy from the ocean, which again, I'll talk about in a minute. So storms are getting more powerful. We're building more near the coastline. The workplace I work mostly is in hurricane forecasting at the short term and how our oceans play a role in that. So where I want to take us is to how we're doing at hurricane forecasting. What I have here is the track forecaster. So this is how good a storm forecast is at saying where a storm is going to go. We have year on the bottom, and we have error. So how good or bad we are. Basically, a high number means we're bad at our forecast, a lot of error, and a low number means we're good. And there's a bunch of different lines for like those lead times. So let's say a weather forecaster makes a 72-hour forecast, so about 3 days. That's kind of like the amount of time you need to make a decision about boarding up your home and evacuating or sheltering in place. So if we look at that 72-hour number, that's this yellow one right here, generally you can see we've been improving. Our error has been going down from about 300 nautical mile error, so in the distance, down to about 100 or actually about 50 nautical mile errors. That's really good. What that means is instead of figuring out which state or region a hurricane is going to hit, so is a hurricane going to hit North Carolina or New York or Massachusetts, we're looking at what football team is a hurricane going to hit at landfall. So we have the Eagles and the Giants here. So that's pretty incredible. That's an amazing improvement in how storms are forecast and how we can prepare for them. We're making those really, really fine decision-making tools for emergency managers, which is great. Now, intensity, the other part of a storm, how strong it's going to be at landfall, we're not necessarily doing as well. So again, the track error is on the left. This is now the intensity error. So this is in wind speed. And again, that yellow line, we started off about 20 nautical miles or knots of air, and we got down to about a little under 15. Air started to come back up. So that means that a wind speed forecast could be off by as much as 15 knots or about 15 miles per hour today. So only a little bit, only like 25% or so increase, improvement in our error forecast. So that's a little worrying. You know, we we know where the storm's going to go, but we still can't tell people how strong it's going to be, which is one of the most important things for the decisions that they make. Now, where does the ocean come in here? So, here's a little schematic about how hurricanes work. Generally, hurricanes can be thought of as like heat engines. So they're these engine systems where they're formed when you have these thunderstorms forming in the tropics generally. They start to rotate because the Earth is rotating. Um, there's warm ocean temperatures in the on the sea surface, and then there's cooler temperatures aloft. And you basically start to transfer heat and energy from the warm ocean into the cooler atmosphere. As you start to suck up that heat, you generate wind and lift and convection. Your warm air comes up, it cools and it starts to spread out. It falls back down and it goes over and over again. So if you have a really, really warm ocean, you can start to basically get that atmosphere supercharged and you get this whole engine system moving. Now, if you have a cold ocean, your storms will weaken and they will start to break apart or de-intensify. What we're finding more recently is we're getting a lot of rapid intensification storms, just like ramping up in intensity very quickly, like Melissa in the Caribbean this past season. Um, when we look at our ocean, here's an example of this from two different storms. So we have Hurricane Katrina way back in 2005, and then we have more recently Hurricane Maria on the right in 2017. These dots are the category of a storm. The map on the back is actually about the amount of heat in the ocean during those storms. And here you can see you have this weaker kind of tropical storm, these blue dots going over this cooler water. And then the moment it goes over this warm pool of water in the Gulf, you get this really, really strong strengthening into a category 5, really, really strong, powerful storm. And then it starts to weaken a little bit, just barely, as it interacts with land and makes landfall in New Orleans. Same thing, Hurricane Maria, you have this warm pool in the Caribbean. So all this ocean heat, you have that storm going over that ocean heat, powering up as it hits Puerto Rico, weakening a little bit, and then actually powering up a little bit again as it goes over this warm pool. So generally, your ocean, like I mentioned, is this heat source, this energy source for hurricanes. That's all well and good. You would think we would know how to bring that information to bear and have a great forecast. Um, but if we zoom out a little bit, we have storms in many, many places, and we know this in New Jersey from Hurricane Irene and Sandy and Ida and others more recently. We have storms in many places where the amount of heat is pretty low. It's not a perfect metric of how strong a storm might be and what impacts it might have. So generally, these tracks are intensification points over these warm areas. But I put a big question mark here. How do we forecast storms that are making it into these mid latitudes? How do we understand the ocean's role in these places? And that's what I'm going to get into for the rest of the talk. So the big question: how do we study hurricanes during this? I cheated here. This is not actually a hurricane. We don't put our students out on boats in hurricanes as much as, that'd be a cheaper method of doing it. I don't have enough waivers to sign, and Rutgers won't let me do that. But I like this picture because it shows kind of like this is actually in Antarctica. It shows the difficult conditions we do work in, and we still won't put our students out in hurricanes to sample in the traditional oceanographic methodology. So we have to come up with some other ways. I'm going to go back in time here, and I'm going to go back to a kind of famous oceanographer from the 80s, and this is Henry Stommel. And Henry Stommel basically wrote a science fiction article about drones that could be deployed out in the world, roaming around the world's oceans, collecting data while scientists and weather forecasters are back at shore. And his kind of bucolic vision was this is on Woods Hole, Cape Cod, Massachusetts, not exactly New Brunswick, New Jersey, but we can flip that on its head a little bit. But it was really kind of visionary in this world. But the important thing is that he partnered up with an engineer and they actually built it. So this is Doug Webb. He recently passed this year, late into his 90s. But he designed this system called the Slocum Glider, which is basically this underwater robot, which I'll go into in a little bit. And he met some of our faculty here at Rutgers back in the late 90s. and actually did the very first deployment of one of those test vehicles in 1999 in Tuckerton, New Jersey, out of Little Egg Harbor. So those of you down south, this was kind of the birthplace of autonomous underwater robots out at our Marine Field Station, the Rutgers University Marine Field Station. And so this is Doug and Clayton, who still with the company. And I think we might still have some of these vessels here, back here, hiding away. So, um, so they did the first deployment. They tied a rope around the tail. It did one single dive underwater, collected some ocean data. They declared success. They pulled the rope in and were super, super happy. 2003 was the first mission where we sent a glider off across a continental shelf, so about 200 kilometers offshore from New Jersey. So New Jersey was really kind of the birthplace of this technology. I'm going to go into it in a little bit of detail of what this is, how the robot works, and then I'll come back out and talk about how we use it for hurricanes. So basically, this is a deconstructed underwater glider. They're run on buoyancy. So basically, they're ballasted to be neutral in the water column, like a scuba diver. And what they do is they have this buoyancy up pump up front, which they'll move back and forth, which I'll show again in another slide. Um, there's the brains of the glider back here, the control board, an air bladder that helps keep the tail out of the water. And then one of the most important pieces is its communications. So there's an antenna back here that has Iridium satellite, cell phone, and GPS and some other communication methods, and then a fin for navigation. So these systems will, oh, and then the other most important part, the science bay. So this is actually the science payload bay that you can swap out, put different sensors. And here's like a temperature and salinity sensor here, which is what we're going to use for our hurricane research. So gliders basically, when they're at the surface, they'll pump, they'll they'll suck in a little bit of water. They'll decrease their volume. That makes them heavier than the ocean that they're ballasted to be in, and they will fall slowly through the water. They have wings on them, so you can see the wings here, and they go down at a pitch angle, and they get a little bit of forward motion. When they get either to their pre-programmed depth or they have an altimeter that'll bounce off the bottom of the ocean, they will pump that water back out and they will increase their volume and become lighter than the water around them, and they'll come back up. And they'll do that over and over again. Um, After about 3 to 6 hours, we have them come to the surface and they'll send their data back in real time. So yeah, this is like an example of a ribbon of data collected by an underwater glider. And I'll get into this. We use this data actually in our hurricane forecast. We want to understand the structure of the ocean underneath those storms, ahead of those storms, and make sure the models are using that data correctly to get the intensity. Gliders can generally operate in water depths of about 5 to 1,000 meters. They can spend up to a year at sea. We're typically out for like a month to 90 days. They can move about 20 kilometers per day horizontally, and then vertically they're going about 25 centimeters per second. So they move about as fast as a baby crawls. They're more like a weather balloon in the ocean, rather than, some like torpedo with a big propeller or something like that. Okay. We use these systems for a lot of different types of research at Rutgers, not just hurricanes. All sorts of things, looking at sediment resuspension, ocean acidification. Grace Saba in our lab looks at that related to how it might impact shellfish. We actually have echo sounders for looking at fish and zooplankton. We have passive acoustics listening for marine mammals like whales. All sorts of science goals. You can swap the sensors out. In particular, I use them for hurricanes. Um, I mentioned earlier that in 2003, basically, we did our first cross-shelf section with one of these systems out there autonomously. Since then, Rutgers has been one of the leading operators of these vehicles. We've done over 600 deployments across the world. We've gone distances of about 8 times around the Earth, if you added up all the distances that we've swam, and about 57 years of our vehicles at sea. So we have about 40 of these vehicles that we've had actually 45, I think, since we started purchasing, building, reconfiguring them. We have about 20 in operation right now. And then most importantly is we establish data pathways. So the data doesn't just come on board to that system. We actually send it off to the National Weather Service in real time, and it gets incorporated into ocean forecasts and models, which I'll get into again. Now, I don't just use one technology for my research. I'm going to talk about gliders mostly today, but we actually have a larger ocean observing network for hurricanes that includes all sorts of different components. We have moored buoys, we have aerial drones, Hurricane Hunter aircraft. I recommend you look up Hurricane Hunter and Melissa video. There's some amazing video of being in the eye wall of Hurricane Melissa off Jamaica. They drop sensors out, they use satellites, radar, um, all these different observing systems that has a story like the one I'm going to tell today about hurricanes. But my expertise is in gliders, so I'm going to focus on that. And I'm going to focus on gliders in two famous New Jersey hurricanes. So these are ones that I mentioned earlier. People probably remember these. We have Hurricane Irene on the left. So this was in August 28th, 2011. I was just a graduate student here at Rutgers, actually for both of these storms. Hurricane Irene was didn't do as much in damages as Sandy. It was about 15 billion in damages. Its track was accurately predicted, but its intensity was really, really poorly predicted, and we'll talk about that. And then I'm going to talk very briefly about Hurricane Sandy, which came just a year later, and it did 72 billion in damages. And again, its track was accurate. Its intensity was actually pretty accurate, but its impacts were underpredicted. We didn't really understand what was going to happen as far as damages at the coast during that storm. Hurricane Irene, I think, yeah. So Hurricane Irene was coming up the east coast of the U.S. in this direction. This is a few days before it made landfall in New Jersey, before it hit North Carolina. We happen to have a glider out, one of our underwater robots out. We do a lot of work for New Jersey Department of Environmental Protection. And so we had one of our robots out for the DEP working on water quality issues, monitoring coastal water quality. And we asked them in advance if we could leave the system out for Hurricane Irene. And they were very supportive. They actually, they were funding us. They had purchased the glider. We had purchased it, but they had supported it. And they allowed us to leave it out and collect data during that storm. We had another glider out up to the north, and I'm not going to talk about too much, but I'm going to talk about this one right off the coast of New Jersey. If people remember Hurricane Irene, it was forecast to be like the storm of the century. It was going to have this storm surge all up the coast. It was going to really damage coastal New Jersey. But in fact, this is in New Brunswick, and a lot of places inland got most of the damages, and it wasn't from storm surge. It was actually mostly from rainfall. So this is the Rutgers boathouse in the Raritan River underwater due to the amount of rainfall and flooding. You can actually see these are rainfall totals all the way up. Some really massive rainfall in New Jersey, some up to like 10. I think that's 10 inches very, very quickly in this region. Now, this is the official forecast for Hurricane Irene. So the black line is what actually happened. That's the best track. The colored lines is like every 6 hours, the National Hurricane Center would make a new forecast, and they would say a storm was going to be this high of wind speed. So in this case, like they were saying, it was going to be up to like 115 knots in a category 4. Well, they kept saying that, but the storm was way down here and much, much weaker on its actual intensity. So it was a bad rainstorm, but it wasn't a bad storm surge storm. Those winds weren't actually as high or being forecast. So there's a famous, Chris Christie was telling people to get the hell off the beach. Rightly so. That was the guidance he had. He was telling people, get the hell off the beach, go inland. People moved inland and they got rained on and they got flooded. And so it was a really complicated issue from both a forecasting standpoint and a public response standpoint. So what happened? What role did the ocean have to play in this storm? So the first part of our observing system that we look at for this is satellite data. So we look at satellite sea surface temperature. This is the temperature of the ocean ahead of the storm. So you can see relatively warm, these reds and greens. You're in like 24 degrees Celsius here ahead of the storm. after the storm, we had this massive cooling of the ocean. So this is like up to 11 degrees Celsius. It only takes about 1 degree Celsius of ocean cooling to actually weaken storms. And we had 11. This is kind of unheard of in the hurricane world. But when we look at some of our ocean features off New Jersey, you might have heard of this feature before in other talks through Ag Extension. But there's this offshore feature called the cold pool. This is a cold ocean water mass offshore that is present in summer. If you ever go to the shore and it's really hot day out and you want to go in the water and you dip your toe in and it feels freezing cold, that's because the cold pool has probably been pushed up toward the coast and actually upwelled at the surface near the coastline. So it's a really common feature. It's also a feature that supports a lot of our regional fisheries, allows some of the shell fisheries to be so good here, and some of the other seasonal species to kind of be able to maintain in this area. This is a cross section, so distance off the coast. So imagine right here off New Jersey out to the coast, and depth. You can see this really warm surface layer of the ocean, and then you have that cold water right below it. This is one of the largest temperature differences in the world of vertical temperature differences of a coastal ocean. This is a really unique feature here in New Jersey off the mid-Atlantic, and then also actually off the Yellow Sea in China and Korea. So I'm highlighting this because this cold water that we saw at the surface of the ocean looks very similar to that cold pool. So we hypothesized that maybe that cold pool actually mixed up and de-intensified Hurricane Irene before it made landfall. When we looked at our robot data, that's exactly what we saw. So this is data from the autonomous underwater glider RU-16. We named them Rutgers University and then a number. And so this was out in Hurricane Irene. And you have this warm upper ocean, cold bottom water. And what actually happened is we got strong currents on the top, moving really, really quickly. And then we got flow on the bottom, and we had shear driven mixing across that layer, driving a lot of the ocean cooling ahead of the eye. We have another ocean observing system called the HF radar, which maps surface currents of the ocean every hour. And here you can actually see the eye of Hurricane Irene before it makes landfall. All this surface water is rushing on shore. So it's rushing on shore quickly, rushing offshore at the bottom. Shear drives mixing and actually cooling of the ocean ahead of the eye of the storm. We found that this was a really significant factor for this particular storm. Now we wanted to connect, does this ocean cooling actually matter to a hurricane intensity and like a storm surge? So we took an atmospheric model, and we used a warm ocean and a cold ocean for our atmospheric model. We took two different ocean conditions, put them underneath our forecast model. And what we found is that when we used a warm ocean, we got a category 1 hurricane for Hurricane Irene. And if we used a cold ocean, we got a tropical storm, so weaker than a category 1 storm. And when we ran that data over a storm surge model, we saw about a 0.25 meter difference in sea surface height or storm surge, basically at the battery in New York City. So you can see the differences here. This red is basically higher water level, and this yellow is lower water level. And so we saw a significant difference in the water levels in those two places just by changing the ocean temperatures. So we published this in Nature, and basically the idea is that the ocean mixed rapidly, cooled rapidly, and that storm de-intensified. That's not the normal processes you see in the deep ocean. Now, a year later, Hurricane Sandy, which I wrote my thesis on, and I'm going to do my entire PhD thesis in one slide here, boil it all down into one thing. Hurricane Sandy did not weaken the way people expected as it made landfall. If people remember, it was a year after Hurricane Irene. The forecast was actually pretty good. Its track, its intensity, 5 days in advance. We kind of knew what it was going to do. We actually had enough time to put out underwater robot offshore in the path of this storm, and that's what I wrote my thesis on, the data from that. And what we found is that Hurricane Sandy came later. So it came in October 29th, so much later in the season. the ocean had already kind of transitioned from this summer condition into this winter conditions, but also it had this weird track. It didn't run up the shelf like Hurricane Irene. It took this crazy left turn and made landfall in southern New Jersey. And what we found is that all of the winds were basically blowing along the shelf toward the southwest. Um, and when you have that southwest wind, it actually does what's called downwelling. So it will push water basically to the right onshore, but then you get a circulation and it'll actually push the lower layers offshore. And it did this much slower than Hurricane Irene. You know, if people remember, Hurricane Sandy took about 48 hours to actually kind of cross the shelf and make landfall. And what we found when we ran an ocean model and when we looked at our glider data is it basically pushed that cold pool feature, what was left of it, all the way offshore of 70 kilometers before the storm actually crossed the continental shelf and made landfall. So Hurricane Sandy, we were kind of like waiting for it to de-intensify and weaken. People were expecting a bad forecast like Hurricane Irene the year before, made some different decisions, but it never actually weakened or de-intensified and made landfall as this really strong, powerful storm in New Jersey. So what did we learn from these two storms? First, these important research questions were actually one cool thing is that they were inspired by data collected from a single glider deployments, from single deployments, one in Irene, one in Sandy. We discovered the detail of these kind of upper ocean mixing. We understood the importance of that cold pool feature to our weather, which was a really big and new thing. And then we connected these upper ocean processes to impacts on storm surge forecasts. So pretty crazy. We just put out two basically temperature sensors during these storms, and we learned all of that from those simple observations. When we started to partner up with different colleagues across the country in these kind of concepts of regional ocean features and how they might impact hurricanes, we went from that one idea of just the ocean's warm and it powers up hurricanes to, hey, there's regional processes and features in every part of our coastal oceans, the Caribbean, the Gulf, the South Atlantic, the Mid-Atlantic, that has a specific character and interesting feature about it for hurricanes. And so we started thinking about how do we sample and understand in all of these places, not just with one or two robots off the coast of New Jersey or in one other place. So the question we had is, could we target vulnerable and uncertain ocean regions to improve forecasts? So briefly, how is our data going to actually have an impact on a forecast? You know, everything I just shared was about how we learn something after the fact. So we started to insert ourselves into the forecast process. This is how a forecast is made for a hurricane. First, forecasts are made by people. National Hurricane Center makes forecasts. Local weather forecast office communicate that to emergency managers. I'll go through the step by step. But generally, how it works is observational data is collected. Number one thing is you need data to make some sort of forecast or understand kind of what's happening in the atmosphere or ocean. Second step, you run your weather models. You collect data, you run your weather models. With that data, you look at where they agree or disagree. That data and model output is analyzed by a human. So humans make forecasts. The National Hurricane Center in Florida is the main group that does that. And then forecasts are issued to local communities. Every 6 hours or so during a hurricane or a disaster, this process is started over and over again. So, so our question was, who and where do we put our ocean data to try to impact this in a positive way? And what we found is that it's really difficult, you know, this is a really stressful environment. It's really difficult to communicate problems with ocean data and ocean forecasts to local communities or to the National Hurricane Center. They're really swamped during hurricanes. So where we started to work is, could we get our data into these into these weather models? And that's the direction we've gone, is how can we improve the weather models so the products that the Hurricane Center are already looking at are improved. So first thing I want to do here is show kind of where these gaps are. This is 3 days before U.S. landfall for many storms. And you can see there's all these storms offshore, but none of them really make landfall in that 3-day window. These kind of grayed out tracks. These are just what we call fish storms. They're way out over the ocean. So that's not our primary challenge. Our primary challenge are these areas in the Caribbean, in the Gulf, South Atlantic, and Mid-Atlantic, those regions I was talking about. These are our landfalling storms where we might need data and we have ocean processes that might be important. If we look at our backbone ocean observing system, these are what are called Argo floats. These are those ocean observing systems that are offshore and that are collecting data for kind of weather and climate all the time. But you can see there's gaps here. There's these gaps here. Let's see, no, it doesn't come up. Gaps here along our coastlines, and this is over a full year. So there's huge areas of blue that we need to fill in with autonomous underwater vehicles or other floats or systems. So we coined what was called the Hurricane Glider Program now. And this was in 2018. So this was kind of our first surge of vehicles. This is on September 11th, 2018. And you can see there were 3 storms in the Atlantic, Florence, Isaac, and Helene. And we had fleets of underwater robots in every single one of those regions during this storm. We had the academic fleet, Rutgers, University of North Carolina, Chapel Hill, Woods Hole was up here. A lot of Navy collaboration. So we collaborate regularly with the US Navy, NOAA, other universities, and even the company that builds the gliders was flying a vehicle way out here off the Cape Verde Islands. So this is one snapshot. But in summary, for 2018, there were 62 community gliders deployed. So huge amount of systems out there collecting data in what were called picket lines and sending that data back to shore. Over time, we've expanded that observing system to fill that gap region. This is colored by year, all the different deployments we've done, Caribbean, in the Northern Gulf, in all of these regions along the US East Coast. And it's something like 600 glider deployments. And we've had them in 38 storms that were making landfall in the US since we first started doing that. 12 major hurricanes had gliders in the 5-day cone, and 92 glider intercepts of named storms. So we've been there for every storm in the ocean since we started doing this. And we've started to gradually increase the amount of deployments we do every year with over 100 in 2024. So we built this observing system. We're continuing to operate it year after year, collect that data. And I mentioned what science we could do with single deployments. Now we're doing similar science with hundreds of deployments and trying to understand the ocean's role in hurricanes. Something new one of my students is doing is moving down into the Caribbean. So further south into the Caribbean, we had a system out. We have these partners with the Caribbean Coastal Ocean Observing System. This is my student, Leah Hobson. We have support from the G. Younger Vetlesen Foundation to deploy systems in some of these regions, international regions where it's more difficult to work outside of the US. And we were flying this system out here, and we happened to be out there during an important time. So this deployment, myself and Scott Glenn, my collaborator, were traveling in Korea at the time with our friend Lev Looney at NOAA. So we're the K-pop hurricane hunters out in Korea. And the amazing thing here was that Lev was helping coordinate aircraft and surface vehicles while we were coordinating this hurricane glider, Leah and my other student Joe, back at shore. And what we were able to do was task the hurricane hunter to actually drop sensors at the glider location as that storm passed within 20 nautical miles of our glider. So this is the closest approach of a glider ever to the eye of a storm. And while it was a Category 5 storm in the Caribbean, intensifying. And we didn't get lucky here, and we also didn't plan for this exact scenario. The idea was that we had enough systems out in the right places that we could retask our systems to be able to sample the ocean during these storms. So we're actively looking at the data from that as we go and doing science on many of the other storms I mentioned. So I'm going to wrap up there. But I really just want to highlight that we went from these kind of simple deployments off of New Jersey that were really important to us locally. And we have now over 60 partners working toward this, US partners, international partners all over the Atlantic, the Gulf, the Caribbean, in the Pacific, off of Asia. We've done sampled typhoons off of Korea, all over the world. And it's really an amazing network of leveraged people that are excited and interested in doing this work that we try to work with. And that was born out of our interest and foresight here in New Jersey, in partnership with the DEP. So a really, really broad reach of what we're able to do when we have that type of support. So I'll stop there, and I'm happy to answer any questions for the remainder of the time.
Awesome. Thank you, Travis. Great work. That really did rock. It's cool to see how much of that was born and championed, led here by Are You Cool, and what you did with a couple deployments, as you said, and where you all have come after the body of research that you've done. We have a couple great questions, and we'll have time for even more. So if you have them, please drop them in the chat. I'll relay them to Travis here during the Q&A break. But I'm also going to launch the poll right now. Please consider taking a few moments to provide your feedback on tonight's seminar and how you might use what you learned tonight. The first question is consent. Yes, if you want to participate. No, if you elect not to. And that should be live on your screens now. With that, I'll go to a question from Jody, who's wondering, why doesn't heat coming off the land not feed into the intensity of a hurricane as the heat coming off the water does?
Yeah, that's a great question. The heat off the land, basically the ocean stays hot like over day and night, and that's the heat capacity of water. So the ocean's kind of like in the Caribbean tropics, it's always hot. The land heats up and cools down really rapidly. So you can imagine, yeah, maybe some heat during the day could go into the atmosphere, and that's actually how you get things like thunderstorms. Kind of late afternoon as the land heats up, you get thunderstorms generated. But for hurricanes, the issue with land is friction. So basically, once your hurricane starts going over land, you basically just have so much friction, which is what we're experiencing in that wind and turbulence and things like that, that storms start to weaken rapidly as they go over things like buildings and houses and mountains and things like that. So there still is air sea heat transfer, but it actually, or air land heat transfer, but generally your land during those storms actually isn't that much hotter or cooler than the atmosphere. So they're kind of about the same temperatures. But oceans, there's really deep reservoirs of heat that, yeah, provide that energy.
Interesting. Thank you, Travis. You explained quite a bit about gliders, but their physics and their capabilities are fascinating. Jody had a follow-up question. Can you talk more about how the gliders keep on track and don't lose signals or get lost during hurricanes?
Yeah, it's a great question. We were really nervous about this actually to begin with. So the gliders generally communicate through a satellite cell phone in their tail. Um, and they are semi-autonomous in that they have a compass and they'll fly toward a waypoint on their own. We don't need to talk to them every moment and able to for them to operate. So we were nervous that we were going to lose communications, and actually, they do quite well. Even in Hurricane Sandy had, I think, 12-meter waves. The glider was in 12-meter waves, so that's what 30 plus feet waves in 40 meters of water. So the glider, though, in that was just basically going up and down in the waves and not actually having too much of a problem. And we actually lost power at our phone that was receiving the calls, and the glider continued to call in. So we were nervous that it was destroyed, but when power came back to our building and where our data center was and where our data came in, it actually we had just missed a bunch of calls. So we've just built up some experience that they do quite well as little kind of floats when they come up to the surface during those storms, and have not had significant issues.
Great, thankfully. Do you ever have trouble with predators or sharks coming after it?
Yeah, not during hurricanes, but that's actually the leading cause of death of a glider is an interesting shark or biofouling from something growing on it, or we've had a squid attacks off of off Sri Lanka. So, but generally we're pretty successful. I think we have a over like 90% success and recovery rate of our systems. So even uh, with those kind of attacks.
Cool. We just had a question pop up. Can you repeat who designed the glider? Who makes them now?
Yeah, the company is Teledyne Webb Research, named after Doug Webb, the engineer who designed the first one. So, let's see. So, yeah, I had him on here. I don't need to go all the way back. I'll go back. He's a great guy. So Doug Webb from Teledyne Research was the engineer who created the system here. Um, and but the idea came from Henry Stommel, a physical oceanographer, who kind of came up with this dream and concept, and Doug was actually the one who implemented it.
Well, you are definitely a real expert on gliders, but I tried my hand at a newsletter for our Earth Day Every Day seminar series. I'm gonna put the link in the chat from February of 2024 if people want to read more about the operations of gliders and some links on where to access data from Are You Cool? Uh,
Yeah, I'm getting some questions as direct messages, so I don't know if you have some, or I could try to answer them too.
oh, okay. Sorry for you to be burdened with those. I best to send them direct to me, but let's go through the ones that you have too in a few moments.
Sure.
Um, So Linda asks, and this comes up a lot in conversations with people throughout the state, can you help guide us on the right terminology of superstorm versus hurricane as it relates to Sandy?
Yeah, I don't think the ocean and atmosphere cares. I think the terms are made societally. And I think they do have some connection to whether a storm is, driven by what's called extratropical forces or whether it's called by tropical forces. But as far as, we at the coast getting impacted, we don't particularly care where they're coming from. Unfortunately, I think there is some insurance decision making that's connected to the name and the type of storm. So if you have hurricane insurance versus wind and hail and like storm surge, all those things have different meanings. So it was kind of a mess with when it was, Hurricane Sandy, as I call it, actually had transitioned into what's called extratropical, according to the meteorologists, as it made landfall, maybe in the few hours before it made landfall. Um, and generally, the biggest issue with that is that it caused a lot of people some insurance issues in how they made their claims. I don't pretend to know the details of why we make those decisions or how, but I think, what I always think about is the atmosphere doesn't care too much what we call them. It's still strong winds, and even nor'easters off the coast can be way more powerful and damaging than weak hurricanes. Winter storms are a big issue for New Jersey and our coast of the Mid-Atlantic bight and flooding. So um yeah.
Uh, Thank you, Travis, for helping to clear that up a bit. A few people noted in the chat, insurance companies, they jumped on that.
Yeah.
Presumably some other local stakeholders who were impacted by such a
Yeah.
storm. A little bit of a sidestep here, but an interesting question from Linda. As bad as hurricanes are, she's wondering what positive effects do they provide land, water, air systems?
Yeah, it's a really interesting question. If you forget about people being impacted, what they're actually doing is redistributing heat from our tropics to our poles. So every year they're basically taking, we warm up our every year in summer due to sunlight hitting the equator. And any heat that doesn't really get kind of transferred northward like it normally should, we can't just heat up the center of the earth over and over again. Hurricanes are actually redistributing some of that heat northward to the poles. Now, there's some other reasons why that might be bad, but that's kind of a normal atmospheric process to kind of move that heat around. There are probably other reasons, other things, around how like coastal forests and ecosystems might be kind of changed or reset. I grew up in North Carolina and was in many storms as a kid and noticed just anecdotally a lot of changes over time due to kind of impacts of hurricanes knocking down dead trees and kind of new things growing. I don't know if there's been any research on that, but it is kind of something off the top of my head. They are a natural phenomenon. I think the challenge is that with our warming oceans and with sea level rise, even storms that are staying the same intensity are causing can cause more damage to our human infrastructure. So I think that's just a big challenge.
Hmm. It's thanks. Interesting question. Never thought about it that way. We hosted a speaker, and you made a bit of a connection there. I think last fall from the state wildlife service, forest fire
Hmm.
management, how that plays an important role in the ecology of progression of forests. So there could be something there with hurricanes too.
Yeah.
Uh, iPhone 3 asks, how much does the type of land topography affect hurricane weakening? For example, mountainous land versus flat grasslands.
Yeah, it can impact it quite a lot. So one real challenge of hurricane forecasting in the Caribbean is that a lot of those islands have very steep topography. They can be kind of mountainous areas, and even some of the parts of Mexico. And it makes it really difficult to predict the intensity of those storms. They might weaken if they go across some of that mountainous topography, which and it's very difficult for our models to resolve that. But generally, the flatter your land and the smoother it is, the less friction, and the more terrain you have, the more friction, and that'll kind of change how a storm might impact a particular region or weaken or not weaken. In the Bay of Bengal, there's some real challenges of, you can go 50 to 100 miles inland and the sea level is you're only still like a meter above sea level. So when it comes to storm surge, you can have storm surges in the Bay of Bengal that go inland, tens up to 100 kilometers from a from a single storm kind of coming in. So yeah, that can be a real issue.
Wow, no doubt. Crazy. Um, we got two more queued up here for you. Sarah and Tim ask, how did the ocean contribute to the huge amount of moisture in Irene that eventually dropped inland?
Yeah, we've done a little bit of look at that. I don't recall, we haven't published anything on it, but I think we did a sensitivity and basically I want to say it was roughly like 10%. The variability between a warm and a cold ocean was about a 10% difference in the amount of rainfall that was happening. But to be honest, in the modeling, rainfall is really, really, really hard to get right. I think it was last year, an anecdote, the head of the National Weather Service, basically every day that he gives a talk on how we're doing, where we're doing poorly at rainfall, he just gets the forecast for that day from somewhere in the US and says, look, this is how bad we are. Rainfall is really difficult. We're trying to understand, very, very small scale, like millimeter scale and smaller processes, chemistry and physics to understand condensation and evaporation. And to get all of that right and to get an accurate forecast is really difficult. And not just an accurate forecast, but like just a few weeks ago, how fast is that rain going to come down? Is it going to come down in, an hour? Or is it going to come down in 6 hours? It's a really, really difficult problem. The ocean, I think, plays a small role in how much basically the wind speeds across the ocean drive some of that evaporation into the atmosphere. And so that's kind of your water source, but how fast it comes down at any particular point and where it's distributed is a really hard thing.
Right on. Maybe some different colleagues who help with that
Yeah,
as well as me. But I got two more for you, Travis.
sure.
Um, Kate and Rick just asked, what about our Jersey wetlands? Are they holding up their own with increased hurricane intensity storms?
I'm not so sure. I think that's a good question for the Rutgers University Marine Field Station is a great long-term monitoring site of things like sea level and weather and ecosystems. They've been sampling at rumps for tens, I don't know, 50 years or so or something like that. So it's a kind of great place to look at data and long-term change. I do know that at that particular site, we're getting more kind of clear day flooding with tides and things like that. Um, but I'm not too certain on, how those ecosystems themselves do. The paper I wrote on ecosystem damages was mostly focused. We found connections between increasing wind speed and like mangrove forests. Now we found that connection because mangrove forests are taller marine ecosystems, and can be really negatively impacted just directly by wind speeds. But as far as, seagrasses and other things that are closer to the ground, it's hard to kind of draw those direct connections because it might be localized flooding or seawater intrusion or something like that. So it's a big challenge. But we argued for more ecosystem observing, not just people observing, but ecosystem observing ahead of hurricanes and storms, because that's, resources that we rely on after storms for weeks and months.
Great, thanks, Travis. And we had some speakers on wetlands in the past, including earlier in this session. So the past recordings are available with a link in the chat. And we're working soon after tonight, which is 4/4, to get all from this fall uploaded onto our webpage. With that, Travis, I'll join the last two questions from Francis and Linda. Francis commented, your slide shows multiple new data point generators for hurricane modeling.
Yeah.
They ask, why is the European model more accurate for weather predictions for coastal storms versus our data points?
Man,
And
they get us every time. They're all using the same data. So I think there's choices on how they run the model, how much money is being invested in the supercomputers. I think the European systems have a large consortium of contributors from a lot of different countries, and they are just really good at it all the time. And we think some of it's around the data assimilation choices that they make. But the interesting thing and the cool thing is all of the data we collect is publicly available to all users, including the Europeans, and all the data they collect is available to us. And so, if the Europeans are doing better, the forecasters will note that, and they'll make advisement in accordance with that. So they use the Hurricane Center uses all available weather products, our own and the Europeans, to make their decisions. The Europeans, it feels like they're generally better than us, but they're not always better than us. And I think it depends on the ocean area that you are in the particular situation. So generally, I recommend relying on a forecaster's interpretation of kind of those different models and data if a storm is impending.
good advice that at the end, they're helpful. So, but the Euro model is actually run by, I thought you confirmed it, but different groups in Europe?
It's run by the European, European Weather Service. I forget the actual name of the organization, but yeah. So they run both their own ocean model and their own weather model, but we're all assimilating and using the same observational data, whether it's a US or whether it's a European model. I think they're a bit further along in how they assimilate the data into their systems, how they actually use the data. But it's all the same data sets.
And a little bit along those lines, the last question I'll cast at you from Linda. How do you estimate that the emergence of AI might influence hurricane predictions?
Yeah, I think it's a really good question. I think in some ways we can have a lot of improve. So AI is generally good at kind of reproducing situations that have been seen before in the data record. AI kind of has to be trained on data and past occurrences. So if we have storms kind of behaving like they did in the past, I think it'll do a pretty good job. But I think there's challenges when you have things like Hurricane Sandy, right? Hurricane Sandy was a storm that made this crazy left turn. It was kind of a black swan event, and it was outside of kind of what you would consider a normal training data set. And so when we have storms like that, I think it's going to have some challenges. So I think there's cool areas of kind of hybrid AI and kind of more historical numerical weather prediction that can be put together, basically hybridized to work to get the best answer we can at any given time scale. I think maybe my last piece on this is I think that we can also use AI at kind of smaller scales within the model, not necessarily to forecast a storm itself, but maybe to get the physics a little bit more right in our model, which can't represent the whole world, perfectly. So there's like these kind of subscale processes that AI is probably going to help with. And we're kind of already seeing that happen and coming on board into some of the different modeling and forecast systems. So yeah.
Mhm. Great. Something to look forward to continue getting improved accuracy and
Yeah.
improving further on what you showed before of all the great accomplishments you guys and gals and your collaborative network have been so far. A friendly reminder, if you're still with us and interested and willing to take the poll, it's still live to provide your feedback for tonight. Much appreciated as we work to continue to improve Earth Day Every Day and other programs. But with that, the great talk tonight by Travis concludes our 4-part series for this fall, which was And What a Wonderful World, an environmental jukebox for New Jersey. As I mentioned a few times, we're working to get all the recordings posted, which will be posted soon on our YouTube page through Rutgers NJES, and that'll be linked on our Earth Day Every Day website. And we expect to also send an email out to everybody who registered, so that way you can go check the recordings out and share them with your friends. Additionally, keep an eye out for more programming we anticipate through Earth Day Every Day. We've done spring and fall since the pandemic. Originally intended to educate people on what you can do at home and to be environmentally friendly and conscious during a pandemic. And we've continued and expanded beyond what you can do from home, but other science-based information and practices you can follow at home and beyond in your communities. So we'll take your feedback and consider what we will cover in next spring. Additionally, we have newsletters that come out through Earth Day Every Day. Keep an eye peeled for more newsletters over the winter before we come back with more seminars we anticipate in the spring. And thank you to my colleagues to help put on the seminar series this fall. I think they're still with us, Sal, Amy, and Steve. Appreciate the collaboration. Everybody, thank you for your participation tonight. And if you made it other weeks, hope you enjoyed the programs. And we look forward to hopefully seeing you at future ones as well. And thank you again, Travis, for a great talk tonight and contributing.
Thank you.
And